Hello everyone, welcome to the video walkthrough solution of Jan 23 Unit 2. Let's look at the very first question. The graph shows how current I varies with potential difference V for an electrical component. When you look at the graph, you see it's a straight line through the origin. Whether it's an IV graph or a VI graph, a straight line to the origin implies resistance is constant, and resistance remains constant when the temperature remains constant. So my answer is C, a resistor at constant temperature. Monochromatic light travels through air and enters a glass block. It means it undergoes refraction. So when refraction occurs, the speed changes, wavelength changes, but the frequency does not change because the frequency of a wave depends on the source. A ray of light approaches a boundary between air and glass as shown. Angle of incidence is I. Question is, which of the following statements about total internal reflection is correct for a ray of light at this boundary? Look at this. Light is traveling from air to glass, as in from a less dense to a more dense medium. And we all know for total internal reflection to occur, light must always be traveling from a more dense to a less dense medium. If light is traveling from a less dense to a more dense medium, whatever happens, total internal reflection cannot occur. So answer is TIR cannot take place. So the equation n lambda equals d sine theta can be used to determine the wavelength of laser light that has passed through diffraction grating. Which of the following is represented by d in the equation? Let's take a look at two diffraction gratings. So of course I cannot draw 100 lines in 1 millimeter, but of course this is something not to scale. This is a few lines in maybe some millimeter, and since it has got more number of lines, so more lines per millimeter. So the distance between two lines is what you call D. This is D. Is the distance between adjacent lines on the diffraction grating. A bat is an animal that locates objects using pulse echo technique. Focus on the echo bit, right? A bat emits a pulse of sound wave that travels to an object. The bat detects the reflected pulse 6 milliseconds later. Speed of the sound is 340 meter per second. Which of the following gives the distance in meter of the object from the bat? So the moment you look at echo, the equation that should pop up in your head is V equals 2D by T. So if you make D the subject of the equation, D should be V times T divided by 2. So if you have 6 millisecond, 6 divided by 2 is 3. And since it's millisecond, it's times 10 to the power minus 0 divided by 1000. That's what makes my answer C. So the V is 340 and T by 2 is 0.003. A light-dependent resistor is connected in a circuit as shown. The intensity of light incident on the light-dependent resistor decreases. We all know if the intensity decreases, the resistance of the LDR increases. And since they're connected in series, if the resistance of one component increases, the voltage across it also increases. So if the voltage across the LDR increases, since they're connected in series and the total voltage must remain constant, the voltage across the fixed resistor must decrease. Number one. Number two is, if the resistance of the LDR increases, the resistance of the entire circuit also increases. So that decreases the current. So the current decreases and the voltage decreases. So my answer is A. Ammeter reading decreases and the voltmeter reading also decreases. The diagram shows some of the energy levels in an atom. Electrons in this atom are excited from the ground state to the energy level N3. So the diagram shows some of the energy levels in an atom. electrons in this atom are excited from the ground state to the energy level 3. How many different frequencies of radiation can be emitted? Focus on the word emitted. So the electron has already been excited to level 3, N3. So how many ways it can drop down? It can directly drop down from N3 to N2. So this will emit a photon. It can drop down from N2 to N1. So this will emit another photon. And it can directly drop down from N3 to N1. So this produces a photon of one frequency, this of the other, and this of the third kind. So there are three different frequencies of photon that can be emitted. So answer is 3. When longitudinal wave passes through a material, compressions and rarefactions are formed. Which of the following statements is correct? So it's better if I show you a diagram like this. Look at this. Here you have a rarefaction and here you have a compression. So, okay, it's better if I show you from here. So here the particles are undisplaced, and when a longitudinal wave passes, you'll see all the particles around the compression move towards the compression, and all the particles around the rarefaction move away from the rarefaction. But at the compression and at the rarefaction, the displacement is 0. Displacement is always 0 at both compression and rarefaction. But at the compression, the particles are bunched up, so the pressure increases. And at the rarefaction, particles are spread out, so the pressure decreases. So that makes the answer D. Rarefactions are points where pressure is a minimum. So let's look at the other options as well. Compressions are points where displacement of particles is maximum. No. At both compression and rarefaction, this is what we just saw here. At both compression and rarefaction, displacement is minimum or 0. Compressions are where point where pressure is minimum. No, compressions are where pressure is maximum because particles are bunched up here. Rarefactions were points where displacement of particles is the minimum. Displacement is not minimum, displacement is 0, not just minimum. Next question. A lamp is connected in the circuit as shown. The cell has negligible internal resistance. In 30 seconds, the charge passing point P is 0.4 Coulomb. Which of the following gives the energy in joules transferred by the cell during this time? So, what do I have here? I have the charge, I have the voltage. So, electrical energy is given by QV. So, charge times voltage gives you the electrical energy. So, 1.5 times 0.4, my answer is B. Question 10 says, which of the following is not a correct statement about stationary waves? Answer is C. The distance between adjacent nodes is equal to one wavelength. The question says not. Be careful about this. So if I draw a standing wave or stationary wave, this is what a standing wave looks like. So here I have my nodes. So if you see, the distance between two adjacent nodes is not equal to the wavelength. It's actually wavelength by 2, lambda by 2. So this is a wrong statement. Distance between adjacent nodes is equal to one wavelength. No, it's half of a wavelength. Question 11 says, a particle traveling at a speed of 9.89 times 10 to the power 5 meter per second has a d Broglie wavelength of 7.37 times 10 to the power minus 10 meter. Deduce whether this particle has a mass equal to the electron mass. The moment you come across d Broglie wavelength, the equation that should come up in your head is lambda equals h by p. So if lambda equals h by p, p should be equal h by lambda. So h is the Planck's constant divided by, I already have the value of lambda. So I get the momentum, and we all know momentum equals to mass times velocity. So mass will be momentum by velocity. I have the momentum from the previous section divided by the velocity. That gives me the mass, which is equal to the mass of an electron. And this is something that is expected of you. You should know the mass of the electron, also the charge of the electron. Question 12 says, in an experiment to determine the refractive index of glass, a student directed a ray of light towards a glass prism. The ray of light is shown before and after entering the prism. Determine the refractive index of glass. Guys, as you can see, the angles that is given in the question are not with respect to the normal. So the very first thing you have to do is draw a normal and then mark the angles with respect to the normal, of course. So this is my angle of incidence and this is my angle of refraction. And once you have these two angles, use n1 sine theta 1 equals n2 sine theta 2. So n1 is of air and the refractive index of air is 1, and the angle in air is 58 degree. And n2, this is what you have to find out, times sine theta 2. Sine theta 2 is the angle in glass. So if you make n2 the subject of the equation, the value is 1.32. Next question says, draw on the diagram the ray of light as it emerges from the prism at A, and no further calculations are required as it emerges. Guys, so when light emerges out of the glass, it is traveling from a more dense to a less dense medium, and when light travels from a more dense to a less dense medium, it bends away from the normal. Next question says, a different prism is made of glass with a refractive index of 1.63. Calculate the speed of light in air. As refractive index is one of those quantities that can be found out using multiple equations. So ratio of sin I and sin R gives refractive index. Ratio of speeds also gives refractive index. So the speed in air divided by speed in glass also gives refractive index. So speed in air is 3 times 10 to the power 8 divided by n is 1.63, that gives the speed in glass. And as you can see, the speed in glass is a little bit lower than the speed in air, because when light travels from a less dense to a more dense medium, its speed decreases along with its wavelength. But we already saw in section A that the frequency remains constant. So question 13 says, equal lengths of two copper wires W and Z are connected in parallel in a circuit as shown. Wire Z has twice the diameter of wire W. Wire Z has twice the diameter of wire W. Okay, so that means wire W is a thinner wire. Explain why the drift velocity of charge carriers is the same value in wires W and Z. So the first point you need to write is Z has a greater cross-sectional area than W. Z is more thick, so it has a greater cross-sectional area. And if the cross-sectional area is greater, so it has a smaller resistance. Why? Because resistance equals rho L by A, right? So resistance equals rho L by A. So if you have a larger area, you'll have a smaller resistance. So Z has a greater current through it because voltage is the same, V equals IR. If voltage is the same, smaller the resistance, greater will be the current. So according to I equals to NAVE, with both A and I 4 times greater than Z, drift velocity is the same. Look at this. I is greater and the area is also greater. So that's what makes the drift velocity constant. For B, wires W and Z are now connected in series. Complete the table by placing a cross in the correct box for each quantity. So we all know that current remains constant in a series circuit. So if they are connected in series, it means the same current flows through both W and Z. So current is the same for both the wires. And since this is thinner, resistance equals rho L by A. Since it has a smaller area, it has a greater resistance. So W has a greater resistance. And in a series circuit, the greater the resistance, the greater is the potential difference. So potential difference across W will be greater. And about the drift velocity, since current is the same, since I equals NAVE, current remains the same. So this has a smaller area, so it will have a greater drift velocity. So drift velocity will be greater. Question 14 says, a student set up the circuit shown to investigate the properties of a negative temperature coefficient thermistor. The power supply has negligible internal resistance. Show that the voltmeter reading was about 6 volt. Ammeter reading is 23 milliampere. So when you look at a question like this, the very first thing you have to do is find out the total resistance in the parallel circuit. So the total resistance of the parallel combination would be 1 by 500 plus 1 by 600 and 1 by answer. So here I have the total resistance in the parallel branch. And if I have the resistance, I know the current as well. Current is 23 milliampere. So the voltage would be V equals IR. So 23 milliampere times the total resistance gives me the total voltage across the parallel branch. Next part, the question says the power dissipated by the thermistor. You have to notice something. So the thermistor is in series with these two, right? So since it's a series circuit, the same current flows through the entire circuit. So 23 milliampere also flows through the thermistor. And since they're connected in series, the total voltage is shared among these two components. If the parallel branch gets 6.28 volt, the resistor will get 12 minus 6.28. So the voltage across the resistor would be 12 minus 6.28 or 6.3. That gives me 5.7. And since it's a series circuit, the same current flows. So power equals VI. So I know the value of the current flowing through the thermistor as well. That is 23 milliampere. So P equals to VI, voltage into this current. So the power is 0.13 watt. Part B says the student decreases the temperature of the thermistor. Explain the effect of decreasing the temperature of the thermistor on the ammeter and voltmeter reading. You have to recall something from your IGCSEs. As the temperature decreases, the resistance of the thermistor increases. So as the resistance of the thermistor increases, the resistance of the entire circuit also increases. If the resistance of the circuit increases, the total circuit current decreases. If the circuit current decreases, the ammeter reading will also decrease. Now, if the current decreases, the resistance of these parallel branch remains the same. And according to V equals IR, if the current decreases, the voltage, as in the voltmeter reading, also decreases. And an extra point would be, since it's a series circuit, and in series, the voltage is shared according to the ratio of the resistance. The higher the resistance, the greater the voltage. Since this now has a greater resistance, the voltage across it would be greater. And if the voltage across the thermistor increases, voltage across the parallel branch must decrease. These are your points. Question 15 says, a student connected a signal generator to a loudspeaker. So here you have a loudspeaker connected to a signal generator. And the thing you need to know about signal generator is it produces a sound, not sound, it produces a signal of one fixed frequency. And so if you feed that into the loudspeaker, it will produce a sound of one specific frequency. The student arranged metal plates in front of the loudspeaker as shown. The student left gaps between the metal plates, and you can guess why there are gaps so that the waves can diffract. Sound waves from the loudspeaker passed through the gaps. The gaps were approximately the same size as the wavelength. See, they are all dropping hints. These are all hints you have to pick up on. The student stood at point X and heard a loud sound. So focus on loud sound. The student walked in a straight line in the direction of the arrow. As her position changed, the sound became quieter. All right. Until she heard no sound. Explain why the sound became quieter until there was no sound. So actually, even though the question says why the sound became quieter, since it's a 6-mark question, you also have to address why the sound was loudest at X. So when does the waves produce a loud sound? When they interfere constructively. And when does constructive interference take place? When the two waves are in phase. And the moment you start moving away from X, oh, by the way, why were the two waves in phase? Because X was the same distance from both the gaps, and the gaps were acting like two separate sources. So since X was in the middle, the waves had undergone constructive superposition or constructive interference at X. And the moment you start moving away from X, the path difference changes, and the waves are no longer superposing constructively. And when at one point away from X, the phase difference is, let's say, 180 degree or pi radian, or the path difference is half a wavelength, then destructive superposition takes place and no sound can be heard. And the question clearly says that you have to construct your answer based on interference. So it's a good thing that the question guides you how you should construct your answer. So these are your points, everybody. So the very first thing is the waves need to diffract. After diffraction, at X, the waves are in phase. So since the waves are in phase, how do two waves interfere when they're in phase? They interfere constructively. So here, instead of writing interference, you can also write constructive superposition takes place at X. That's also acceptable. And when you are moving away from X, the path difference changes. So I think in the mark scheme, they gave this as an option. Either you write about path difference or about phase difference. So just to say on the safe side, I wrote path and phase difference, both changes. So no sound is heard when destructive interference takes place. And you know this by now. When does destructive interference take place? When the waves are in antiphase. Let's move on to the next question, next part of the question. Part B says, interference can be demonstrated using visible light. A student connects two filament lamps to the same power supply. Okay, a screen is placed a distance from the lamps as shown. Explain why it is not possible to create a consistent interference pattern on the screen using this arrangement. So you might be wondering, if this works over here with sound, it should also work with light. But the issue is you're using two different sources. So two different sources very likely will not have the same frequency, meaning they are not coherent. And to get a stable interference pattern, you have two requirements, and you should know this by now. What are the two requirements? for waves to undergo a stable, or waves to exhibit a stable interference pattern. Number one is waves must be coherent. And what does that coherent even mean? They must have a constant phase relationship. But if you're using two separate sources instead of one, there is absolutely no way the light from the lamps would be coherent. And if they are not coherent, the phase relationship is not constant. Question 16 says, an irrigation system uses a pump to move water from lower level to higher level. The electricity for the pump is generated using panel of solar cells. The panel of solar cells is 1.2 meter long and 0.8 meter wide. To pump water from the lower level to the higher level, the pump needs a minimum power of 140 watt. Guys, the moment you see the pump needs a minimum power, so what type of power does the pump require? Electrical power, of course. So this 140 watt is actually electrical power. But where does this power come from? This power comes from the sun. And the moment you see intensity, the equation that should pop up in your head is intensity equals power by area. And in that equation, intensity equals power over area, this power is always in the form of light. Remember this. So the moment you come across these quantities, that is intensity and the dimensions of the solar cell, so using these dimensions, you can easily find out the area. And using the equation intensity equals power by area, you can find out the power. But this power will be in the form of light. But the power given over here is the electrical power. So when you talk about the efficiency of the solar panels, it takes in, as in the input is light and the output is electrical. So when you calculate efficiency, it's always the energy output divided by energy input, or efficiency can also be calculated using power. It's not always just the energy that you'll have to use to calculate efficiency. You can also calculate efficiency using power as well. So the very first step is to find out the power of the sun at the solar cell. Intensity equals to power by area. So power equals to intensity into area. But guys, one more time, the power that you have calculated over here is actually in the form of light. And the output power is already given in the question. So efficiency is output by input. And one more time, output by input doesn't always necessarily have to be in the form of energy. Output and input can also be in the form of power. So this is my efficiency. Next question says, suggest two reasons why the value calculated in one is the minimum efficiency that will operate the pump. Why is this the minimum efficiency? When it comes to solar cells, the light radiation that falls on it must be incident perpendicularly. If the light radiation is not perpendicular, you'll never get the maximum power output. So this could be one of the reasons. Intensity may be lower due to clouds. Okay, this could be another reason. And the other one would be light from the sun may not be incident on the solar cell at 90 degrees or perpendicularly. Part B says light from the sun arriving at the solar cell is unpolarized. And part B1 says explain the difference between unpolarized and plain polarized light. This is one of the most common questions, but unfortunately, despite being one of the most common questions, a lot of time students mix up two terms. They mix up direction and plane. Just remember, for this answer, you either construct your answer completely based on plane, or you construct your answer completely based on direction. For this paper, I have constructed the answer based on plane. So in unpolarized light, oscillations are in multiple planes. And in plane polarized light, oscillations are only in one plane. And this gets you 2 marks. The third mark is for linking the direction of motion with the plane. So the plane includes direction of motion or direction of wave travel. But guys, if you were writing the same answer in terms of direction, the answer would have been, I'm saying this, unpolarized light has oscillations in multiple directions. Plain polarized light has oscillations in only one direction, and this direction is perpendicular to the direction of wave travel. So you clearly see when it comes to plane, the language is plane includes, and when it comes to direction, you say direction is perpendicular. For this paper, you can clearly see it's laid out perfectly clearly in the mark scheme. The first section is for plane, the second section is for direction. My request to everyone would be, do not mix the two concepts up. Keep them separate. Either you construct in terms of plane or you construct in terms of direction. Next part says, describe how a student can demonstrate that light from the sun is unpolarized. Okay, for this I have a small demonstration for you all. So here you have unpolarized light at the left, of course. And when unpolarized light passes through a polarizing filter, you can see it gets polarized. Now, if you start rotating the filter, you'll see, since there are multiple directions of oscillation or multiple planes of oscillation, even if you rotate this, at least one plane will always pass through the filter, right? So there will always be one plane of oscillation that gets to pass through the filter. So even if you rotate this, since one plane always passes, rotation does not cause any change in intensity. So that is the key concept behind how to check whether light is unpolarized. Pass the light through a polarizing filter, rotate the filter, and if the light is unpolarized, there will be no change in intensity. Why? You don't have to write this part, I'm just saying this anyway, because at least one plane of oscillation of light gets to pass always through the polarizing filter, in whichever orientation it is placed. So my answer is light directed through a polarizing filter. This gets you point 1. And the second point is there is no change in intensity. And guess what, guys? Had light been polarized, the rotation of the filter would have caused a change in the intensity of light. And the moment you see that the intensity changes, rest assured this is polarized light, not unpolarized. So when it comes to, one more time, unpolarized light, when unpolarized light is passed through a polarizing filter and rotated, there is no change in intensity. Question 17 says, a student set up the circuit shown to determine the EMF and internal resistance R of a cell. I is the current in the circuit and R is the resistance of the variable resistor. Show that for this circuit, R equals EMF by I minus R. Forget what the question asks you to show. Just look at the circuit. This internal resistance and the load resistance are connected in series, right? So this EMF will be shared among these two. So this EMF will be equal to IR plus IR. Since they're connected in series, the same current flows through both this load resistor and this internal resistor, right? So EMF equals to IR plus IR. So if you just make I common, if you take I common, so that then it becomes IR plus R. And then you send I to the other side and make R the subject, and this is what you get. Part B says, student varied R and measured the corresponding values of I. The student then plotted a graph of R against 1 by I. All right. So if you look from here, R equals EMF by I, and actually, I have to refer to this actually. So R equals EMF by I minus R. So R equals EMF times 1 by I minus R. And this is in the form Y equals mx plus C. If I am plotting a graph of R against 1 by I, so the gradient of the graph, since it's in the form Y equals to mx plus C, the gradient of the graph will give the EMF and the y-intercept will give the internal resistance. So from here, the question has to find out the EMF and R for the cell. So like I said, first you have to find out the gradient of the graph and then the y-intercept. As you can see, the y-intercept is -2. And if you take the gradient, it will be this value. So the internal resistance is 2. Of course, resistance cannot be negative. So internal resistance is given by the y-intercept. And if you take the gradient of the graph, the value should be 1.5, gradient of the graph. And please make sure while you're taking the gradient, you always use a large triangle. So I can show you how to take the gradient. So I can take these values. I can take the entire graph. So this is my change in y-axis. So change in y-axis would be 10 minus -2. 10 minus -2, change in y-axis, divided by change in x-axis would be 8, right? So 10 minus -2 gets you 12, divided by 8. 12 by 8 is 1.5. And since it's the EMF, the unit should be volt. Next part of the question says, the student suggested that the power dissipated by the internal resistance R decreases as R increases. All right? Comment on the student's suggestion. Always remember, these two are connected in series. So if R increases, the current in the entire circuit decreases. And according to P equals I square R, the current through the internal resistance also decreases, right? So if I decreases, R remaining the same, the power dissipation decreases. So the student is correct. Next part of the question says, the student added a second identical cell in series with the first cell and repeated the experiment. Add a line to the graph to show the results of the experiment. So when you add a second identical cell, what happens? In series, right? So the EMFs add up. So now the EMF will be twice as before. And since the whole thing is still in series, the internal resistances also add up. So the internal resistance will also be doubled. So when you add another cell in series, both of these values will be doubled. So EMF is doubled and internal resistance also doubles. And EMF was given by the gradient of the graph. So what does it look like when the gradient is doubled? The graph becomes more steep. So this is what the graph should look like. EMF is doubled, as in the gradient is doubled, and previously the internal resistance was 2. Now the internal resistance has been doubled, so that makes it 4. Question 18 says, in an experiment to demonstrate the photoelectric effect, ultraviolet light is incident on a metal plate. Photoelectrons are released from the plate with a maximum speed of 3.51 times 10 to the power 5 meter per second. Calculate the energy of these photoelectrons in eV. So guys, once you have the value of speed, it's expected of you to remember the value of the mass of an electron. Once you have the mass and the speed, you can easily find out the kinetic energy using half mv squared. But once you do that, you'll see that the value comes in joule. But the question clearly says to calculate the value in electron volt. How exactly do you do that? Always remember the value in joule divided by 1.6 times 10 to the power minus 19 gives you the value in electron volt. So all you have to do is just divide this value in joule by 1.6 times 10 to the power minus 19. The value comes to 0.35 electron volt. Next part of the question says, the table shows typical values of work function for 4 different metals. So these are the values of work function. The ultraviolet light used in the experiment had a wavelength of 310 nanometer. Deduce which of the metals was most likely to have been used as the metal plate. So if you get a very basic idea of the photoelectric effect. What happens in the photoelectric effect is you have a metal surface and there is an electron on the surface. A photon comes in. If the photon energy is greater than the work function of the metal, the electron is dislodged, electron is emitted, and it is emitted with an energy. What energy does it possess? A kinetic energy. So this metal surface has a work function. So all of this comes from this photon energy. So this is the famous Einstein's photoelectric equation. That is, the energy of the photon is equal to phi plus the kinetic energy. And for this specific question, since the wavelength is given, you can easily find out the energy of the photon using E equals hc by lambda. And for this kinetic energy, you already have the value from the previous question. This is the value of the kinetic energy. So all you have to do is just make phi the subject of the equation. So my very first step would be to calculate the photon energy using E equals to hc by lambda and then make phi the subject of the equation. And once you see the value, you'll see that this value of phi is closest to magnesium. So the metal must be magnesium. For the next part, question says, photoelectrons are only emitted from a given metal surface if the frequency of the incident radiation is above a particular value. Always remember that one photon releases one electron. In other words, you can say each photon only interacts with one electron. So the electron absorbs the energy from the photons. A minimum energy is required for the electron to be emitted. And do you remember energy of the photon in terms of frequency according to E equals to hf? Higher photon energy related to higher frequency. So frequency of radiation has to be above a particular value. Next part of the question says, a student makes the following statement. It does not matter what the value of the work function is for a particular metal. Photoelectrons can always be released if the intensity of light is high enough. Intensity of incident light is high enough. Criticize the student's statement. Of course, the student is wrong in this context because what is intensity? Intensity is the amount of photons arriving each second. So intensity is related to the number of photons arriving per second. And when it comes to photoelectric effect, each photon interacts with each electron. So the intensity also determines the number of photoelectrons that will be released. So intensity is related to the number of photoelectrons per second. But the energy of these electrons, but the energy of the photons does not depend on the intensity. Intensity does not affect the energy of the photons or the kinetic energy of the photoelectrons. What do these depend on? The energy of the photons as well as the kinetic energy of the photoelectrons depend on the frequency of light according to E equals hf.